Hello friends, in the previous lectures we have been considering the relation that exists between polar and Cartesian coordinate system. Now we began our discussion by considering two-dimensional Cartesian coordinate system and its equivalent in the spherical coordinate system, which is the polar coordinate system. Now we compared the Cartesian, two-dimensional Cartesian and two-dimensional polar coordinate system, and we were able to show that when we consider the coordinates of each of this system as a function of a function, then we will be able to recover the corresponding independent variable. So the coordinates of the polar system would be r and theta. The coordinates of the Cartesian system would be x and y. Now we were able to express r in terms of x and y, theta in terms of x and y, and similarly the coordinates of the Cartesian system, x in terms of r and theta and y in terms of r and theta. Now we were able to show that when the r, the coordinates of the polar system, is expressed as the function of x and y, and this x and y in turn is expressed as r and theta, function of r and theta. So what essentially we have is r as a function of a function, then we are able to recover r, which is the independent variable. This r in the right hand side is a function of a function. This r is an independent variable. Similarly, it goes for the theta. A theta is expressed as a function of x and y, and this x and y is in turn treated as the function of r and theta, and now we are able to recover the corresponding variable theta. The same goes for x and y as well. We treat them as the function of a function, and we are able to recover the corresponding independent variable. Now, from this we stated that when we are able to recover the corresponding independent variable by treating the coordinates as an elongated function or a compounded function, we said both these coordinate systems are inverse of each other. So we are expressing the coordinates of a system as a compounded function, and we are able to recover the independent variable of it and the independent its corresponding independent variable. Then it allowed us to claim that these functions or these coordinate systems are inverse of one another. To substantiate that claim, we consider the Jacobian of each of these coordinate functions. So we translated the coordinate systems, their corresponding coordinates, into functions, and we consider the Jacobian of it if J1 be the Jacobian of the polar system, the polar coordinate system, and J2 be the Jacobian of the Cartesian coordinate systems. So the Jacobian, again, it rather presents the partial derivative of the coordinates with respect to the corresponding variables. So in this case r and theta, we will have the variables is r and theta, then depends on x and y. So that is what the partial derivatives of r and theta in terms of x and y will be expressed as Jacobian 1. Partial derivatives of x and y in terms of r and theta, Jacobian 2, and we are able to show that the product of J1 and J2, it yielded as an identity matrix, which meant J1 is the inverse of J2. Now the inverse kind which we postulated from this relation, we were able to substantiate by considering the product of the Jacobians. Now in our previous lecture, what we essentially did was, instead of considering this well-established coordinate system, we considered a generic coordinate system of I, j, k, along with I prime, j prime, and k prime. So in I, j, k coordinate system, with that of the prime coordinate system of three different coordinates encompassing or representing the three-dimensional system, we began this consideration of the generic coordinate system with the function I, again as a function of I prime, j prime, k prime, which are subsequently the function of I, j, k, j prime being the function of I, j, and k, the k prime being the function of I, j, and k. So this ultimately it yielded us the corresponding independent variable I. So I treated as the function of I prime, j prime, and k prime, and each of these prime coordinates again further treated as the function of I, j, and k. This subsequently yielded us the corresponding independent variable. This when extended to j, k, and subsequently I prime, j prime, and k prime. So all these when expressed as the function of a function. The coordinates of both these systems when expressed as the function of a function, it yields the corresponding independent variable of j, k, I prime, j prime and k prime. And this, when we start off from this point and when we consider the Jacobian of, here the j1 is now the Jacobian of the I prime, j prime and k prime coordinate system, and j2 be the Jacobian of the I, j and k. We were able to show that when we start off with this consideration, we were able to show that the same inverse relation that we observed for r and theta is also either established for these two sets of coordinate system I, j and k, I prime, j prime and k prime. So essentially this Jacobian relation, the inverse that is established between the Jacobian, is not particular for the r and theta coordinate system or polar and Cartesian coordinate system. It can be established for any generic systems as well, or any generic coordinate systems as well. That is what we established. Now what essentially the Jacobian captures is, the Jacobian principally it captures the partial derivative of this coordinate system that we have considered with respect to the corresponding variables that describe it. So the coordinate system, it helps us describe or it helps us define a point in the space, and this coordinate system, if we assume this coordinate system to be a variable of another coordinate system, a variable of another certain variables, or it varies with certain parameters. Now the Jacobian, it essentially captures the variation of this coordinate system based on these parameters, how this coordinate system would vary based on these parameters. So that is essentially what this Jacobian captures, and the inverse of this Jacobian is being yielded. So the inverse of this Jacobian, the one Jacobian is the inverse of another for the different coordinate system that we have considered, is established by this relation here. So this inverse relation is established for two coordinate system, and this inverse relation that is established by the Jacobian is nothing but the partial derivative of this coordinate system with respect to the corresponding variables that dictate it. You have a coordinate system that is dictated by, or that is influenced by the variables, and the Jacobian, it captures the partial derivative of this coordinates with respect to its variable. And when you consider two coordinate systems and you are able to establish the Jacobian of two coordinate system, the inverse relation is established between these two coordinate systems. Now when we want to make sense out of this inverse relation that is established between two coordinate systems or two Jacobians of the coordinate system, then we need to make sense out of the individual entities of this Jacobian, which is the partial derivative. Let me repeat. We have established the inverse relationship between two Jacobians, and each of these Jacobians, they correspond to each or one of the two coordinate systems that we have considered. When you look closely into these Jacobians, all that they comprise of is the partial derivatives. Now when I say I have to attribute a meaning to this Jacobian in order to gain an understanding out of it, what essentially I am doing is I am attributing a meaning to the entities of this Jacobian to gain an understanding out of it, to gain a physical understanding out of it. So when I say entities of the Jacobian, it is nothing but the partial derivative. So what essentially we need to do is we need to understand what these partial derivatives are to make the sense of this inverse relationship between the Jacobian. So Jacobian, partial derivative, when you make sense out of the partial derivatives, then we will be able to make use of the inverse relation that is established between the Jacobians. Good. Now let us consider a point in a space. So let us consider a point in a space. Now if I want to describe this point, like in this case we have a white sheet of paper, rather virtually, and we want to describe the point in the space, and one way of doing that would be introducing a coordinate system. Let us assume that we are introducing a polar coordinate system, or rather a Cartesian coordinate system, and based on the Cartesian coordinate system we will be able to describe what this point is. One other way of doing it would be, it is possible for us to assume an origin anywhere. So let us assume an origin here, and it is possible for us to drop a position vector r, and this position vector, which has a magnitude and a direction, can help me understand or can help me describe the position of this point. So all that I need when I want to use a position vector to describe a point in the space, all that I need is an origin. From that origin I will be able to drop a vector in the two-dimensional space, and this vector comprises of a direction and it comprises of a magnitude. Then based on that I will be able to describe the point in the space. So this point in the space is based on the position vector r. So this point in the space is described by the position vector r. Now what essentially we have is, we have considered this position, this point in the Cartesian coordinate system. So before considering the vector r to represent this point, we have considered this point in the two-dimensional coordinate system. So we consider a point. In order to describe the point, we start off with the two-dimensional coordinate system. We said that there is another way of doing it, and that another way would be using this position vector. Now when you consider this point here, this vector here, what essentially it means is, this point, which is already can be expressed in terms of the Cartesian coordinate system, can then be used to describe the nature of this vector. So this point, which can be used or which can be defined using the Cartesian coordinate system, can also be used to describe this vector that dictates the position of the point. So we said that there are two ways of describing a given point. One is using a position vector r, the other is the coordinate system x and y. Now what we are trying to do is, we are trying to merge these two and express the position vector in terms of x and y. So this position vector, it indicates this point here, and this point is expressed in terms of x and y, and we are merging these two. So r vector, it indicates the point here in the space and with this origin, and this point is also defined by x and y. Now since we are merging these two coordinate system, that is a random vector and the two-dimensional Cartesian coordinate system, the r vector is expressed in terms of x and y. So this r vector, now we have expressed it in terms of x and y. This r vector, it dictates nothing but the position of the point in the two-dimensional space. Now let us consider a point that is close to the point, the original point, the one in the black, a point that is close to this original point, and this point is along the x-axis. So what is varying is, I am considering a point that is close to the original point here, and this point is defined using the coordinate system, the Cartesian coordinate system, as x plus delta x, comma y. So I am considering a new point, and this new point, the coordinate system is x plus delta x, the Cartesian description for it is x plus delta x, comma y. So the x component has changed, not the y component. When you drop the position vector for this new point, it would be of this form here, and this new vector, the one in the red, will be of this form, x plus delta x, comma y. So the position vector that is required, so you are starting off from the same point. Now the position vector that is required to describe my new point would be x plus delta x, comma y. Now when I take the difference, so these are two vectors, one vector pertaining to x and y, the other vector x plus delta x, comma y. When I take the difference between two vectors, r of x plus delta x, comma y, minus r of x, comma y, when I am taking the difference between two vectors, that is one in the red and one in the black. So the red is x plus delta x, comma y, and the black is x, comma y. So this one will be in the red, this one in the black. Now when I consider the difference between these two vectors, the difference of these vectors will be pointing in this direction. So it will be pointing in this direction. So if I use a different color for it, it will be pointing in this direction. So this will be the direction along which the difference between these two vectors are pointing. Now if I consider the magnitude of these vectors, so what essentially I have is, I have considered 2 points, and I have considered the position vectors of these 2 points, and I have considered the difference between the position vectors of these 2 different points, one in black, one in red, and I am introduced 2 vectors to describe the black point and the red point. I am considering the difference in the position vectors that I used to describe these 2 points, and that gave me this expression, and the difference between these 2 points is pointing or is along the red arrow direction. The difference between these 2 vectors is along the along the green arrow direction. Now if I assume that this delta x is nothing but the magnitude of this green vector. So what essentially we are doing is, the black point, we are moving delta x along the x direction, and we reach the red point, and we have a position vector describing the red point, a position vector describing the black point. We are considering the difference between these two, and we have the direction of the resulting difference vector, and we also have the magnitude of the resulting difference vector, which is delta x. Okay, so delta x, it stems from how we were able to how we were able to describe the red point. So the delta x, it comes from the difference between these points and these points, and the red point is nothing but delta x away from that of the black point. There is no change in the y direction. So now when I take the ratio of the difference in the position vector and the magnitude of that vector. So what essentially I am doing is I am considering the difference in the position vector and the magnitude of the vector, the magnitude of the difference in the position vector. So then what essentially then this would be is nothing but the delta x, because we are just changing along the x-axis, not the y-axis, and the delta, the red point is designated as x plus delta x. Now then what this expression here then would mean, this expression here, which wherein only the x is changing, the y is remains the same, so therefore I have written as just in terms of x. This is nothing but the partial derivative of the position vector when it is varying with respect to x with respect to the corresponding variable. So you have a position vector and it is varying with respect to x. We have selected a point in such a way that it is varying with respect to x, and we have considered the partial derivative of this position vector with respect to that variable. And now when you consider this relation here, we have a vector and we are taking it, and we are taking the ratio of that vector with respect to its magnitude. So ultimately this should yield us a unit vector. Let me repeat, what we have done is, in this case we have considered the difference in the vector, which is a vector. So we have considered the difference between two vectors, which is a vector, and in the denominator we are taking the difference in the two vector, we are taking the ratio of this difference in the two vector with respect to the magnitude of this vector in the denominator. So what essentially then we would get is, we would get a unit vector that is pointing along the direction of the difference in the two vectors, that is pointing along the direction of the difference in the two vectors and has a unit magnitude of length. So therefore in the context of the two-dimensional coordinate system of x and y, this vector then subsequently be our I vector. So the one in the green would subsequently be our I vector. So what essentially we have done is, this I vector, we have arrived at this I vector, the unit vector, by considering 2 points and by considering these 2 points in such a way that one point is just delta x away from the other point. The y remains the same. Now we have considered the difference in the position vector that describes these 2 points, and we have taken the ratio of this difference in the position vector with respect to its magnitude, and this gives us the unit vector along the green direction, and this green direction is a unit vector and it is parallel to x-axis, and this is what we refer to as the unit vector. So unit vector I, and this unit vector I is nothing but the partial derivative of, so since from this expression we have written it in this way, and this is equivalent to nothing but the partial derivative of the position vector with respect to x. So ultimately now we have an expression, for a generic expression for the unit vector I. If you could recollect, or whenever you consider the description of a unit vectors in the Cartesian coordinate system, that is I, j and k, the way it is introduced is, even we in the initial lectures, in the introduction lectures, the way we introduce the I vector is, we consider that I vector is a unit vector that is pointing along the x direction. So that is the description that we attributed to I vector, and this description was exclusively based on the Cartesian coordinate system. Now here what we have done is, we have considered a point and we have considered a neighbor of that point, the corresponding neighbor of that point, and we were able to describe the point and its neighbor using a position vector, and when we consider the partial derivative of this position vector with respect to its neighbor, then we were able to arrive at the unit vector. So here again, what the ratio is important. The numerator gives us a vector, and so it means it's also, in addition to a magnitude, it also gives us the direction, and this direction is delta x. So the one in the green arrow here, it shows us the direction of this difference in the position vector. Again, this difference, the direction comes from the difference in the two vectors, which we saw in our introductory lectures. And in the denominator, what essentially we are considering is the magnitude of these difference vectors, and that is nothing but the delta x. And since we are considering the ratio of a vector with respect to its magnitude, the end goal, it will be equivalent to a unit vector pointing in the vector direction. So it is a vector that is pointing in the green direction. Since our discussion is based on the Cartesian coordinate system, since the position vector is described based on the Cartesian coordinate system, we have given the name I. So here the I vector is not a vector that is along the x direction, but it is a partial derivative of r, the position vector, with respect to its corresponding variable. Now the r vector is one way of describing the point, and the x is rather one coordinate of the Cartesian coordinate system. I hope you are able to see the relevance between the entities of the Jacobian and how these entities now relate to the individual unit vectors of a coordinate system. So the r vector we used to describe a point, and this occurs in the context of the Cartesian coordinate systems. Therefore we have the variables x and y. Now it is possible for us to arrive at the same way the other unit vector. Again, if you begin with the Cartesian coordinate system, so this is our x and this is our y, and we consider a point here, and we start off with the origin, and this point is r. So this point is described by r vector, which again can be expressed, since we are superimposing, we are considering the r vector in the context of Cartesian, and that's the reason why we are treating it in terms of r and theta. Now when we consider a different point, and this different point is x and y plus delta y. So this different point is of the same value of x, plus but the y has changed. So the corresponding position vector will be r vector x of y plus delta y. Now when I consider the difference between r vector of y, that is of x comma y plus delta y, minus r vector of x and y, then the difference between these two will be along this direction here. Now when I take the ratio of the difference between these two vectors with respect to its corresponding magnitude, then what essentially we would end up with is rather the vector that is pointing along the green arrow but of unit length. So I am considering the difference between these two vectors, and then I am taking the ratio of this difference with respect to its corresponding magnitude. So essentially then I would have a vector, and that vector would be pointing along the green arrow direction, and it will have a magnitude of, it will have a unit magnitude. So what essentially then I would have is, I would have described the j vector which is along the y direction. Now this expression can be rewritten as r of y plus delta y minus r of y divided by, so this difference is nothing but the delta x, because we have considered the point in such a way that this difference in the magnitude, the magnitude or the magnitude of the difference in the vectors is nothing but delta y. So it will be delta y, and this overall expression is nothing but the partial derivative of the position vector with respect to y, and that ultimately yields us the corresponding unit vector. So what essentially we mean is, when we take the partial, in this case when we take the partial derivative of the vector, one way of describing a point, with respect to the corresponding variables associated with another coordinate system. In the previous cases I, j, k, I prime, k, j prime and k prime, here r vector and x, y. When we consider the partial derivative of r vector with respect to the variable that describes another coordinate system, we combine both these two. When we take the partial derivative of it, we have shown that it leads us to the corresponding unit vectors. Now, when we want to arrive at or describe these unit vectors in such a way that the length scale of this unit vector should not have an influence of the components, in this case, the length scale of the unit vectors depends on the delta x and the delta y that we have considered. So here, the length scale of the unit vectors, when we define the unit vectors as the partial derivative, the length scale of these unit vectors depends on the delta x and the delta y, the length scale associated with the delta x and the delta y. So in this case, the length scale associated with j unit vector is dependent on the delta y, and the length scale associated with the I unit vector is dependent on delta x. Now, when you consider a physical system, and when you are rather selecting points to find out the nearest neighbors, then this nearest neighbor, the scale associated with the nearest neighbor, will be the scale that you will use to describe the unit vectors. Okay, let me repeat. When you consider a system that is in a system on the range of meters, you wouldn't and you are considering it and you are start analyzing it, you wouldn't go and consider the neighbor that has several orders, a neighbor that is several order, that is in the order of micrometers, to find the nearest neighbor. That will be too rather you will have to zoom in too much, you will have to put in effort too much in order to distinguish, in order to resolve one point from another, if we are considering a nearest neighbor in terms of micrometer for a system that is of meter size. So essentially then what you would do is, you would consider a nearest neighbor in the order of say 0.1 meters, 0.2 meters or 0.01 meters. When you do that, the delta x and the delta y will be of the range of 0.1, 0.2 or 0.01 or similar of the sort. And when the delta x and the delta y are of the order of the system that you are considering, the kite correspondingly means that the unit vectors will adopt the same description. The unit vectors will adopt the same description. If we are operating on the system on the meter scale, the unit vector will adopt the same length scale. If we are operating in a system on a micrometer scale, the unit vector will adopt the same scale. So we are not externally imposing a length scale to the unit vector as we would do in the usual case, but when we have such a description where the unit vectors are nothing but the partial derivatives of the position vectors, we have arrived at these unit vectors by considering the partial derivatives. In this case, the length scale is rather implicitly assumed and it is rather consistent. So it is consistent with the system and we don't have to externally impose any unit to these unit vectors. And this unit comes from how we consider the neighbors, and since the neighbors that we consider would be for a given scale would be of the range of the scale, will be in the order of that scale, the unit assumed by this unit vector, the length scale assumed by this unit vector rather will be of the same order. So we do not have to externally impose any length scale to it. And again, this is possible because we have arrived at these unit vectors by considering the partial derivatives. Secondly, you might wonder, like, this entirety of this position vector, the position vectors in its entirety, the size of the position vector, it depends on my position of the origin. So depending on what my position of the origin is, depending on where I select my origin to be, the length of my position vectors would vary. So if my origin is this, the length of my position vector would vary. That's absolutely right. But even though the length of my position vectors vary depending on my origin, what essentially we are focusing on is not exclusively the length of the position vectors, but rather the difference in the lengths of the position vector. So even if I start from this point, even if I start from the point in gray, the difference in the position vectors indicating the point in red and the point in black would remain the same. Even though my origin is different, even though the magnitude of the individual position vectors are different, when you consider the difference in the vectors that are used to describe the point in black and the point in red, when you consider the position vector, the difference in the position vector that is used to describe this point A and point B, irrespective of the origin that you choose, would remain the same. So therefore, what we have done is, we have considered the position vector that is superimposed on. So position vector in itself will help us describe the position of a point, the location of a point in a space. So here the position vector, it helps us describe the location of a point in a two-dimensional space. So this in itself acts as a coordinate system. And the other coordinate system we have introduced is the Cartesian, two-dimensional Cartesian coordinate system x and y. Now we were able to superimpose these two, and we were able to take the partial derivative of one coordinate system, that is the position vector, to that of the variables of the other coordinate system, and this partial derivative helped us arrive at the unit vectors that can be used to describe any position at the point. So that can be used to describe the position of this point, and therefore the significance of the partial derivative becomes clear here. So when you consider the partial derivative of the one coordinate system with respect to another coordinate system, what we essentially then would end up representing it is rather the unit vector that forms a basis of this one. So when you consider or when you combine these two operations or these two representation, these one wherein you have a change along the delta y, and here wherein you have a change along delta x. So what essentially you have established is you have built a coordinate system at the point, at the black point which we have initially considered. We have established a coordinate system at this point with unit vectors I and j, and these unit vectors, even though they align along the x-axis and the y-axis, now we have a different name to it. So by considering the partial derivatives, what the partial derivative essentially yield is, these partial derivative, it helps us establish a coordinate system at a given point in space, and the direction of the coordinate system and the magnitude of this coordinate system, the direction of this unit vector and the magnitude of the unit vector is rather governed by the partial derivative, and that is rather that which forms the individual element of the matrices. Now what essentially we have done is we have considered r vector in the context of Cartesian coordinate system, and that's the reason, even though we were able to arrive at a different set of unit vectors, we are able to define our own unit vectors. We gave the name as I vector and j vector. The same operation can be extended to rather polar coordinate system. Now supposing we should begin with a point again in space, and this point is defined using a position vector r, and instead of superimposing this position vector in Cartesian coordinate system, I am considering this position vector. Another coordinate system that I'm introducing is polar coordinates r and theta. Then what essentially I would have is, I would have this point being represented, if this is my origin for it doesn't seem hit here, if this is my origin for my r and theta polar coordinate system, then this point would be represented in this manner, and this point would be r and theta. So this point would be r and theta. Now what essentially can be done is the similar operation. So we can consider neighbors along the r, and so to make it a bit more legible, so we can consider neighbors along the r, and we can consider neighbor along the theta. So what essentially it means is I can consider a neighbor in this direction, the one in the red, and the distance between these two is, or this one in the red is represented by r plus delta r comma theta. This point in the red is designated as r plus delta r theta, and I can also consider another point, say green here, and this green point is rather r comma theta plus delta theta. So what I have done is I have a point in black, and that is described using the position vector r, and this position vector we are considering it in combination to another coordinate system, that is the polar coordinate system. So therefore the position vector r can be described in terms of r and theta. So the small r radius and theta the angular coordinate. Now we are considering two neighbor points. So one neighbor point in red, it is along the r axis. It is along the r axis. So this one neighbor point in red is r plus delta r comma theta. The theta hasn't changed. Now this point in green is along the theta. So only the theta varies. Now in this case, the unit vector along this direction, the unit vector along this direction, pointing along the red point. So this would be r vector r plus delta r minus r vector, which is of r, the original point, and the magnitude of this difference will give us the unit vector that is pointing along the red direction. And unlike I and j, we cannot introduce the same notations here. So what notation that is generally used is E1 vector. So when you are defining a vector at a given point in space, and this point is not defined by the Cartesian coordinate system, so the generalized way of representing it would be E1 vector. And in the same way it is possible. So this E1 vector can also be, for our understanding, treated as ER vector. So this is pointing, so this means that the radius, the radial component of it is changing. The same expression can be extended for the theta. So here the variable is theta, delta theta minus r of theta, and we are considering the magnitude of it minus r of theta, and this would give us another unit vector. And since this neighbor, usually the neighbors are close to one another, the direction of the green one will not be rather inclined, it will be in this manner, in this way. So you have your orthonormal coordinate axis, one in green and one in red. So the slight change here, even though the graphically it is bit apart, so ideally it will be close to one another. And if you consider this, what essentially has changed is just delta theta has increased, and this is the direction along which it points at. So what then we have is, we have two coordinate systems, ER and E theta, or we have two different orthonormal bases, ER and E theta, that are rather described by considering the partial derivative of r with respect to the specific variable. So in this case, ER unit vector or E1 unit vector is partial derivative of r with respect to the radial component. The partial derivative of r with respect to theta is the other unit vector. So these unit vectors, they form the basis of their own. So these unit vectors, they do not gain their description, they do not gain their definition from the existing polar coordinate system. They gain their definition at a specific point, and the partial derivative, the variation of the position vector with respect to around that point. So that is how these unit vectors, they gain their definition, and these unit vectors being perpendicular to each other, they form a basis of their own, and these are often referred to as the covariant bases. So what these bases introduce is a covariant basis, and this covariant basis, it depends on the point that we consider. So what essentially we have done is, to describe a vector at a given point, we develop our own basis. So depending on the point, so we have a vector notation at each point. So supposing we have a flux, so if we consider a domain, a two-dimensional domain, and we have here, so it is not a Jacobian, it's a flux. At this point we have a Jacobian, rather a flux at this point, a flux at this point, and so on and so forth. At different points we have different fluxes, and in order to describe each of these fluxes, we are essentially introducing the coordinate system at each of these points. So what we are doing, instead of using a unified coordinate system, we are introducing coordinate systems at each of these points, basis at each of these points. We are introducing orthonormal bases or bases at each of these points, and this we are able to do it because we have established the partial derivative, the way of describing the unit vectors using partial derivative. So what essentially we are doing is, now instead of defining a flux based on a singular, based on one basis, we are now able to define a basis at a given point and define the vector based on this basis. So we have J1 flux here, J2 flex here, J3 flex here, instead of having a uniform description, instead of having a single or a fixed coordinate system to describe all these different flexes, what essentially we are doing is we are introducing bases at each of these points, and the way we are able to do it is by through these relations, and these bases are called as covariant bases because they vary with the point, and using this basis we are now describing the vector at each of these points. So essentially that is what we have established, and this is what we mean by the covariant basis. Now one way of getting rid of changing the components based on a fix. So when you have a fixed basis and when you are considering the changes in the overall basis, then we have to correspondingly change the components. In this case what we are doing is we are introducing the basis for a given point. So therefore all the vectors are based on that particular basis. So this vector is based on the basis that is built here. The J2, that is the flex. The J1 or the flex at this point 1 is based on the corresponding basis that is built there. This flex J3 is expressed based on the corresponding basis that is built there, and the way we build the corresponding basis is by considering the partial derivative of it with respect to the original, with respect to another coordinate system that is rather established or that can be considered overall. So if I have to describe this flex in this two-dimensional system, if I assume, for instance, if I consider for the overall description, if I consider Cartesian coordinate system, then I can consider the combination of Cartesian coordinate and a position vector or the direction of the flex in this each of these points here, and then I will be able to build my own basis, and this basis will be referred to as the covariant basis. So Cartesian to describe the entire system, and for each of the points we build our own basis, and this we refer to as the covariant basis. And whenever in an application we see that this J vector is pointing in this direction, or the J vector is pointing in this direction, or so on and so forth, it is possible that this direction can be expressed based on the covariant basis. This directions can be expressed based on the covariance. So if you see a representation of this form, J vector is pointing this direction, and so on and so forth. So these directions, it is possible for us to describe these directions based on the covariant basis. It is possible that these directions have been achieved through introduction of the covariant basis. Now, before proceeding further, before looking into the other aspects of the covariant basis, let us consider a simplistic example. With this we will wind this lecture up to understand the importance of this basis. Now, supposing we have an arc of this form, and a vector in this arc is described by the arc length. So a vector in this arc is described by the arc length. So this arc length, let us assume it to be s rather. So from this point we have a finite curve, and depending on what the value of the s is, be it here, be it here, be it here, the corresponding vector would vary. So there is a vector associated with this arc, and the vector associated with this arc varies with the arc length. Now if we want to find the unit vector of this vector, supposing we have consider this point here, and at this point there is a vector t, and this vector, it has a magnitude and direction, and it is dependent on the arc length s. So there is a specific arc length assumed here. So when I say arc length, this is the point origin, so this is arc length is 0, and when I say arc length, I am considering we are we are describing is a point in this arc. So what essentially we are doing is we are describing a point in this arc. Instead of using a coordinate system, we are describing a point in this arc, in this curve, using the arc length. So this point here, it would mean the value of the arc length is s1. So on and so forth, we have considered a point here. Now at this point, if I want to the vector at each of these points, it depends on the arc length. So that is the condition we begin with. Now the unit vector, or when I want to introduce, when I want to describe a unit vector for this vector, what I can do is I can consider the set of operations that I performed earlier. I can consider an position vector R, and this position vector R is dependent on S. Now I can consider a neighbor, and that vector would be along delta S, so it will be L plus delta S. Now the unit vector, the corresponding unit vector T cap would be something like R vector S minus delta S by R vector S divided by the magnitude of it, S plus delta S minus R vector of S and the magnitude of it. So this is nothing but the partial derivative of R vector with respect to S. So this gives me the unit vector, that gives us the direction along which the T vector is pointing. So what essentially I have done is, we have considered just a curve, and the coordinate system to describe each of the point in the curve is nothing but the corresponding arc length. And when the vector associated with this curve, it varies with the arc length. And what essentially we have done is, for that particular vector, now we are able to identify the unit vector. That means we are able to identify the direction. Now the question is it possible for us to introduce a basis that is similar to that of the basis that which we normally introduce? Is it possible for us to introduce a basis that we normally introduce, an orthonormal basis? So in this case we are considering a two-dimensional system, and instead of describing the vector using the arc length, because for the translation, for using this vector for any other application, we need to describe it in terms of the conventional basis. For instance, this could be an example of a flux along the grain boundary. So the flux along the grain boundary can be expressed in terms of the arc length. So this flux along the grain boundary can be expressed in terms of the arc length. Now on the other hand, the flux that is occurring within the grain will be expressed in terms of the bases that are orthonormal to one another. So the flux along the grain boundary can be expressed in terms of the arc length, but the flux along the within the grain, it needs to be expressed in terms of the covariant basis, or we need to at least express in terms of the orthonormal basis. Now when we have to do that, then in that case what essentially we need to do is we need to introduce an appropriate coordinate system. Of course this coordinate system need not be Cartesian, it need not be polar, we can introduce any coordinate system. So when we introduce, say, a generic coordinate system which we can refer to as Z1 and Z2. So let me recollect. So what essentially we are doing is we have a tensor that is dependent on the arc length, and this arc length is rather subjective. It needs a specific arc, it needs a specific curve, and it is subjective. Now what we want to do is we want to translate this vector to a different way. We want to express it in a different manner that is rather involves the basis that we are familiar with, the orthonormal basis that we are familiar with. So in order to introduce this orthonormal basis, we are considering a generic coordinate system, and the relation between this generic coordinate system and the orthonormal basis which we have established earlier, that is nothing but the partial derivative of the position vector with respect to the corresponding coordinate of the system. This would yield us one unit vector. It would yield us one unit vector, that is E1 prime. So this x1 can be replaced by x, then it will yield me I vector. This x1 can be replaced with y, it would yield me j unit vector. Now instead of considering x and y, which would be, we are considering Cartesian, we are considering z1 and z2, it can be anything. So what we end up then having is a generic unit vector. In the same way, the partial derivative of the position vector with respect to the other coordinate will yield us another generic vector. So what we have done is we have now two bases vector that we are familiar with, that we can understand. So two bases represented by E1 and E2, these are two rather vectors, two unit vectors, and these two unit vectors, they correspond to the generic coordinate system Z1 and Z2. Now what we have established is the vector component, the unit vector component of the T vector that we are interested in is this, and this Now we have also established that the position vector is also dependent on the generic coordinate system that we have introduced. So essentially it means that the r vector is a function of z1 and z2, which are in itself a function of s, and this we are considering the partial derivative. And now what can be done is the chain rule can be applied. So essentially it would mean z1, and this would be not a partial derivative but the ordinary derivative ds plus the partial derivative with respect to the cosecant coordinate. Now we have already established now this term, the partial derivative of the unit vector with respect to coordinate is one of the unit vector, the partial derivative of the position vector with respect to another coordinate is another unit vector. So ultimately the vector that we are interested in is the derivative of the coordinate system that we have considered with respect to the arc length and the corresponding unit vectors, dz2 by ds p2. So what essentially we have done is we have combined, or we have expressed a vector that is rather subjective to that of the arc length using the conventional basis of E1 unit vector and E2 unit vector. So we have a conventional basis that is represented by E1 and E2, and using E1 and E2 we have represented rather a specific, a unique form of a vector that is restricted to the curve, and that is described by arc length. So that is one benefit of having this generic description, this covariant basis of describing or introducing these covariant bases while describing a vector. So I believe this has been a bit large lecture, so we will wind this up and we will continue, and we will see how this understanding lend itself to another numerical operation that will be a vital part of our material research. Goodbye.